So I want us to work through some problems together real quick. And they are 6.1, number 40. So we're going to be just trying to think things through in our minds with counting. So chapter 6 is about counting. So do you feel like you're pretty good at counting? Do you remember when you were younger and you had to and sometimes you tried to count to like 50 or 100 or whatever and see how far you could count? Well, now we're counting to like even cooler things than that. So 6.1 number 40 says, how many subsets of a set how many subsets of a set of 100 elements have more than one element? By the way, we've already talked about how many subsets there are several weeks ago of a set of a certain number of elements. But this asks us how many subsets of a set of 100 elements have more than one element. So you can talk with each other and just think about if you can think of a strategy for how to figure out how many subsets of a set. So let me give you an example with, let's just say, 3 elements. So if you have a set of 3 elements, the subsets of that are the empty set. So there you could take nothing out of that, right? If you didn't like anything, like for example, if you ever had a stubborn child or known as a stubborn sister or brother that doesn't like anything, so they choose nothing. You could also choose just A, you could choose just B, you could choose just C. Or you could choose 2 things like A and B, or you could choose A and C, or you could choose B and C, or you could love it all and you could choose all 3, A, B, C. That's how many subsets there are in a set of 3. How many of those subsets have more than one element? Right. So there's 4 that have more than one element. Now, obviously, if you have 100, if you went A, B, C, D, E, F, G, if you had 100 different things, you'd have many, many, many more subsets, right? But it's actually pretty easy to figure out how many subsets only have 1 or less elements in them, though. So how many subsets of a set have 1 or less element in them? If you know that there's n things in the set, how many subsets only have 1 or less? So this is n equals 3. Well, think carefully about how many subsets of a set have 1 or fewer elements in them. Correct. Smart. So that was easy. But what does everybody else think? Do you agree with that? There's always n plus 1 subsets that have 1 or less elements. Right? So how many subsets of a set of 100 elements would have 1 or less elements? Right. So the total number of subsets is equal to the number that have 1 or less element plus the number that have more than 1 element. Hold on, that has more than 1. Now we already know that we already know how many elements have 1 or less element in them. I mean, we already know how many subsets have 1 or less, which is what? 101. But we don't know how many have more than 1 element in them, so that's X. So this is a review. How many of you can remember from several weeks ago how many subsets there are in any set? So look down at the example of 3. How many total choices could you pick out of the set of 3 things, including everything from nothing that you chose to choosing everything? From nothing to everything, how many subsets were there in a set of 3 elements? If you count them all. There were 8, right? And if you had 4 elements, let's just say if I went to this problem and I added option number D, so instead of saying ABC, I had D. You could actually repeat all of these same 8 choices without even using D at all, right? Or you could choose D and then you could repeat those same other choices as well with D. So there'd be twice as many options if you added if you added a 4th element, right? So every time you add one more element, you double the number of choices you can make. So it's times 2. So what's the pattern going on if there's always twice as many elements? If there's always twice as many choices of subsets every time you add one more element, then how many total choices are there? So if you double every time, what's the formula for that? You multiply by 2 again and again, n times what's the total? So this right here is 8, right? 8 subsets, which is equal to 2 to the third. How many subsets would there be in a set of 100 elements? 2 to the 100, right? So we know that this equation is true, that the total number of subsets in a set of 100 elements is equal to the number of subsets that have 1 or less plus the number that have more than 1, right? Because those are mutually exclusive, right? So therefore they have to add up to the total amount because you either have one option or the other. Just like the number of people in the world that's less than 6 feet tall, plus the number of people that are 6 or more feet tall equals the total number of people in the whole world, because you have to either be one or the other. So we know this number right here is 2 to the 100, right? And we know the number that have 1 or less is 101. And we don't know how many have more than 1. So can I use algebra to solve that equation? How do I get x by itself? Subtract it. Yeah, so the answer is 2 to the 100 minus 101 Dalmatians equals x. Like that. So that's the solution. There's 2 to the 100 minus 101 subsets in a set of 100 elements that have more than one element in them. Okay, that was pretty cool. Now that you're getting practice, I'll see if you can do even more of it on your own on the next problem. Let's try number 48. Work on 48 together. I'll flip back to the section of the book. Okay, so this one's going to be fun. Would you rather be in a wedding getting married or be in a wedding taking pictures of the people getting married? You can pick your role, I guess, in this problem. So 48, it says, in how many ways can a photographer at a wedding arrange 6 people in a row from a group of 10 people where the bride and groom are among these 10 people? So the 10 people include the bride and groom. But the 6 people don't necessarily have to include the bride and groom. But then there's a couple of stipulations, though. If the bride must be in the picture, then what could happen? How many options do you have to arrange the people? How many ways are there to arrange them? How many arrangements can be made? So if you have to have the bride in the picture and you're picking 6 people out of the 10 people, and the 10 people includes the bride and groom. So let me put that in parentheses. I misspelled groom, by the way, including bride and groom and the 10. Just to make it clear that the bride and groom don't have to be in the 6 necessarily, but they are some of the 10 people though. So how many arrangements are there of 6 people from 10 people, including the bride and groom and the 10, if the bride must be in the picture? What do you think? What do you think?
I'd be like picking 5 people from time, right?
What?
It'd be like picking 5 people from time.
Basically, except although you'd still have 6 different spots you could put the bride in though.
Right.
Do you remember when I taught you last time how to do the word Mississippi? Is there any way that we could try to use the same strategy to calculate how many words we could make, like out of the word Mississippi? Would that work?
What word would you,
What?
like what word?
Well, that's the critical question. So we would have to do something like this. So there's one person who's the bride. We have to represent the bride uniquely because they're the bride. Then the groom doesn't matter. We didn't say anything special about the groom. He may or may not be in the picture. But then we need 5 other people to be in the picture, right? So I'm gonna say C, 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 C for chosen in the picture. Then the other 4 people are not chosen, right? Like that. So,
Don't put the word in?
well, the groom doesn't matter because you see, if we define who the groom is, then that means that, so we're gonna calculate how many ways there are to arrange 6 people out of this group of letters. Although I might be making this a little too complicated though. Because this section 6.1, you're actually not supposed to use the actual like specialized counting rules for it. But first, before I do that though, let me consider a simpler case. What if you forgot about the bride and you just wanted to know how many ways there were? This is called a binomial process. If you wanted to know how many ways there were to choose 6 people out of 10 and that you didn't have anything about the bride and groom, but you wanted to know how many ways there are to choose 6 people out of 10, you could do it like this. 6 people get chosen like that. 4 people do not get chosen like that. So 6 people get chosen, 4 people do not get chosen. How many ways are there to make a word out of that? So notice that if you're chosen, you're the letter C. If you're not chosen, you're the letter N. How many ways are there to? So this person represents like maybe Tom, Sally, Jerry, Jill, Bob, like a bunch of different people, but you don't know what their names are. But each of them, whatever letter, if you move the letter N and the letter C around, just like move them around to a different order, then maybe Tom gets, if there's a letter N on Tom, then maybe he does not get chosen. So basically, you can't how many ways you can arrange the letters C and N. That's how many different ways there are to choose the people that represent the C's and the N's, right? So this would represent how many ways there are to arrange to choose 6 people out of 10 people. Forgetting about the whole bride thing, if that makes sense. Does that make sense? Somewhat. And by the way, this would equal 10 factorial. Remember how we did it last time? 10 factorial over what? Right, exactly. And that's called the binomial coefficient, or that's how many ways there are to choose 6 things out of 10. So if you 6 things out of 10 would work like that. Okay, perfect. So now that when you include the bride in it though, you still have 4 people who do not get chosen. So those are like the ends. But the bride always gets chosen. So instead of labeling the bride as like as like a C, just like everybody else, they're called like a B. Pretty much. Does that make sense? Okay, now, I'm not sure if it even makes sense to me even, but. Okay, let's see if we can figure it out though without using the letters. Let's just see if we can think through it logically. Because we're not really supposed to use those letters, I don't think yet. Until you have a little bit better grasp of process. So if you choose it, let's say you choose the bride first. Let's say you choose the bride first. So how many choices do you have to put the bride in the picture? If you have 6 spots to choose from, like left, right, second to left, second to right, next to the left side of the middle or the right side of the middle. 6, right? So you have 6 choices to put the bride. 6 choices to position the bride. Yeah. And then you have 9 more people to choose from, right? 9 more people to choose from. So how many choices do you have so once you've chosen the bride, you have 6 choices. You can put them first, second, third, or fourth. Then how many other places do you have to pick for? 5, right? 5 more positions. How many choices are left to put somebody in then one of those 5 positions? Now those positions don't really have names, but we could name them position A, position B, C, and D, and E. How many choices do we have remaining to put somebody in position A? Of the 5 spots that are left. Well, once you've taken the bride out and put her in a spot, that spot's taken. So how many other people are left after the bride's gone out of the 10?
None.
Right. And then how many ways are there left after that person has been put in a spot? How many other people can be put in the next spot?
Eight.
Right. And remember the fundamental counting principle is that if a process consists of several different sub-processes and there's this many choices in each sub-process, the total number of options for the whole process is the number of things in each sub-process multiplied together, right? So 6 times 9 times 8, and then how many people are left to go in the third remaining spot?
So
And then 6, and then 5, right? So you basically have 6 positions to put the bride in, and then you have 9 choices to put somebody in spot A that remains, and 8, 7, 6, 5, like that, right? Does that make sense? Okay, perfect. Okay, good job. Let me think about this. 9, 8, 7, 6, 5, and then times 6. Okay, cool. Now let's try, if both the bride and the groom must be in the picture, how does that work though? So B, if both the bride and the groom must be in the picture. How many choices are there in that case? How many choices are there if both the bride and the groom must be in the picture?
6 times 5 times 8 times 7, 6 is 12.
Yes, I believe that's right. 6, you have 6 spots to put the bride. You have 5 spots to put the groom, because you can't put them in the same spot the bride already is. And you have 8 people left. So you have to pick 4 of them, right? So there's 8 choices to put one of them, then 7 remaining, then 6 and 5. That looks good to me. What about if exactly one of the bride and the groom is in the picture? So if the bride and groom are not both in the picture, but only one of them. Exactly one. This is a dumb way of saying it though. Exactly one of the bride or the groom. Does that make sense to you? exactly one of the bride or the groom.
6, 8, 7, 6, 5, 4.
So you have 6 putts to put the bride, and then you only have 8 choices left, you're right. Because you're not choosing the groom. Right? But that's only half of the answer though. Because you could also, so remember there's 2 options that could, this is like the very first problem we did where we have the number of subsets that included less than this or more than that. This is how many choices you could do if they did include the bride. Plus, you also have to count the choices that included the groom. So if you chose the groom instead of the bride, you've also put the groom in 6 different spots, and then you can't choose the bride, so you only have 8 people left to choose from. So then you'd have that. Right? But an easier way of doing that, since these numbers are actually the same, there's just as many ways to choose the groom and put them in the picture as there are ways to choose the bride and put her in the picture. It's really just double. So you could also just take double. This is equal to 2 times the whole thing. 6 times 8 times 7 times 6 times 5 times 4. Like that. Okay, perfect. Well, let's think about another question. Let's think about 54. 54. This is now all of these are important counting principles that we're learning. So every student in a discrete mathematics class is either a computer science major or a mathematics major, or both. So some students are jointly majoring in computer science and mathematics. So either computer science or mathematics or both. And it says how many students are in the class. So how many total students are there? How many total? If you know that there's 38 computer science majors in the class, and you know there's 23 mathematics majors in the class, and there's 7 who are both jointly majoring in math and computer science. So let's break these down. The 38 computer science students equals the ones who are just CS majors only, but within that 38, it also includes those who are joint majors, right? Those who are both. I'm gonna take out the word both because that sounds like maybe different thing. Sorry. I'm gonna say joint instead of both. The just CS majors and then the joint majors who are both majoring in math and computer science. And the 23 people in the class who are mathematics majors includes those who are just mathematics only, but it also includes all the same people who are jointly majoring. So, and of course, the number who includes both, that includes just those who are joint majors only, right? So we can break those numbers down like that. 38 CS, 23 MM, 7 both. How can I use those three breakdowns to calculate the number total? The total number of students in the class. So the total number of students in the class can logically be broken into 3 categories. What are the 3 categories that it can be broken down into? So think about how to make them mutually exclusive. How do you make things that not have any overlap?
Subtract the 7 for both.
Yeah.
So the total is equal to the number of totally distinct separate students. So how can I express it without any overlap? It'd be the ones who are just CS students, plus the ones who are just math students, plus the ones who are doing both, right? That's the total. But how can I calculate what the total is by using those 3 overlapping numbers though? So let's just see, if I took the number. If I took this number. Plus this number. So 38 plus 23, but that's not the total, right? So let me cross that out. I don't want to make you think it's the total. If I took the number that are just CS plus the number who are joint plus the number who are just MM plus the number who are joint, this right here would represent 38. This right here would represent 23. Now that does not represent the total, right? But what if I have just CS plus joint and I have just MM plus joint? What can I do to those four terms so that it only has three terms left in it instead of four?
Subtract.
Subtract what? One what?
Joint.
Joint, yeah. So since I have two copies of the word joint in that, if I say minus the number that are joint, so it's kind of small. So if I say just CS plus joint and just MM plus joint, if I subtract one joint, it'll cancel out the extra joint and I'll just be left with just CS plus just MM plus joint, which does equal the total, right? So that number can be broken down into 38 plus the 23 minus the 7, and that actually does equal the total. So the total equals 38 plus 23 minus 7. And they call this in counting, sometimes they say that the number of things that are in set A and B together is equal to the number of things that are in A plus the number of things that are in B plus the number of things that are in A and B together. That also works for probability as well. The probability of something happening, like two different things that can happen, the probability of having one thing or the other thing happen is equal to the probability of the first thing happening plus the probability of the second thing happening. Oh, so I didn't even say plus. Sorry, that's supposed to be minus. My fault. Minus the probability that they both happen together. A intersect B. Like that. That's because the probability that this thing happens could include sometimes that B happens as well. The probability that B happens could include sometimes that A happens as well. So this is like saying just A plus the ones that are joint. This is like saying just B plus the ones that are joint. So you have two copies of the joint events in these. So if you subtract one copy of the joint event, then you'll end up with only one of each. And that'll be the total. Okay, so we figured out problem 54. And then I think they had one more problem I wanted to go through with you, and then we're ready to start doing some more actual cool formulas and stuff. So 6.2, number 4. Okay, let's think about this one. This is going to be a good mind twister. A bowl, or sometimes I've heard this as like a dresser, like with socks in it. But a bowl contains 10 red balls. A bowl has 10 red balls. Because it's a dresser drawer with 10 red socks. In fact, the way I've usually heard it is that it's dark in your room and you're trying to get socks out of your dresser drawer. You want to make sure that you get at least one pair of socks that's the same color. But this book just talks about balls. So a bowl has 10 red balls and 10 blue balls. A woman selects balls at random without looking at them. Okay, so question A. How many balls must you select to be sure of having at least 3 balls of the same color? So how many do you need to select blindly to be sure of having at least 3 that are the same color? So you're reaching into this bowl and you're closing your eyes and you're picking out balls, how many do you have to pick out to make sure that, yeah, at least 3 of them are the same color, either red or blue?
Was sure me
100% sure. Yeah.
13.
Okay, that's close. 13 is close, but this is not quite asking the question that you're thinking about. So it doesn't say at least 3 that are red. It doesn't say at least 3 that are blue, which actually would be 13. It just says at least 3 that are the same color. 5, yeah, right. Because 5. So think about this. 5 is equal to an odd number plus an even number, right? If you have 5 balls, okay, well, explain to us why you said 5. Maybe you probably could explain it better in a fresher way.
Okay. So since you need 3, just went to the number right before 3, which is 2.
Yeah.
Multiply that by 2. Added 1 because that's the threshold.
So I think what you're thinking about is, imagine the worst case scenario that you got unlucky and you never got more than 1 ball in a row, right? So if you got several balls in a row, then you get them quicker. But if you only got like 1 red one and then 1 blue one, and then 1 red one and then 1 blue one, if you never got matches, if you got as few matches as possible, you'd still get a match on the 5th one, right? And even if you start with blue and then red, and then blue, then red, and then blue, you'd still have a match on the 3rd one. And if you did have 2 or more in a row, then you get one even quicker. Like if you got like red, red, blue, red again, then you'd have them in only 4. But you're guaranteed, even if you had as many possible that were different colors as possible, you'd still always get at least 3 of the same color on your 5th pick. So you're right. So the answer is 5. You have to select at least 5 blindly. But then part B says, how many do you have to pick to be sure of having at least 3 blue balls? So how many to be 100% sure that you have at least 3 blue balls? And then this time what you said, Zoe was right. You have to have at least 13 because in the worst case scenario, whoops, what did I say, 10, 13. The worst case scenario, you could actually, it's a very small chance of happening, but you could end up getting all 10 red balls at the first. And then even if you got 12, you still only have 2 blue. So in this case, you do have to get at least 13 in order to be 100% sure of getting at least 3 blue. So there's a big, huge difference between that, right? That's like why if you have a specific birthday, like what are the chances that 2 people have the same birthday in the class that I do, like my specific birthday, that's pretty low. But there's actually a much higher chance that 2 people have any birthday that's the same among themselves. Like if you have only about 35 people or so in a class, then there's actually a more than 50% chance, I think, that there's at least 2 people with the same birthday out of all of those. So if you don't specify like exactly what color it is or what birthday it is, then there's a lot higher of a chance of a match than if you do specify the color. Okay, well then let's go ahead to, we're going to narrow it down actually a little bit. So we've been talking in general terms, but one of the most common things that happens is called permutations. And the second most common thing is called combinations. So let's briefly talk about those both. Okay. Both of these can be expressed using those letters that I was talking about. So permutation means that things are distinct. Things are distinct. So like you choose one person to be president of the FSO. Do you know what the FSO is? Falcon Student Organization, or SGA. How about Student Government Association? So you choose one person to be president, one person to be secretary, one person to be treasurer. Like you have different distinct roles. In that case, you have n total people, and you're choosing R of them. That's equal to n. You have n people you can choose for the first person times n minus 1 dot 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 times n minus 2. You keep on going until you get to a total of R choices being made. Does that make sense? Now, that's not a clear mathematical definition because you can't just tell people keep going until you get to R. Like this isn't a computer programming language exactly. I mean, math is kind of a computer programming language, but you don't have a computer to run it with, so you have to be more precise. What's a more precise way of saying that you go to exactly R choices? And then you stop or whatever after R choices. So like what does it mean, for example, if I say that I have 8 students and I'm going to choose 3 of them to be president, vice president, and treasurer? What does that mean? That means that I have 8 people I could pick to be president of the club. Then there's 7 more choices left to be vice president, and then there's 6 more choices left to be treasurer, and I've stopped after picking 3 people, right? That's what that means. Except is there a way of defining that without just telling them that there are choices, like there's an actual mathematical fraction that I can use? What do you think? Yeah, there is, because I could just to say it's 8 factorial over, how do I cancel out the last 5 numbers that I didn't include? The 5, 4, 3, 2, 1.
Subtract 3 from the 8. You find
Yep, subtract the 3 from the 8 and a 5 factorial on the bottom. Right. Or in other words, you'd have 8 factorial on the top, 5 factorial on the bottom, and then the 8 factorial represents 8, 7, 6, 5, 4, 3, 2, 1. Boom, all the way across. But the 5, 4, 3, 2, 1 at the end of that would be canceled out by the 5 factorial on the bottom, so then you just have 8, 7, 6 left. So the definition of P and R is equal to n factorial divided by n minus r factorial. But just remember though, if you're programming this in code, never, ever, ever use this definition of the factorial, or you will be wasting huge amounts of computer time. Because the truth is, you should never calculate the full factorial of the top, and you should never calculate the full factorial of the bottom and then divide them into each other. That's totally inefficient. The only way you should ever program the permutations calculation is just simply to do a loop and just multiply n times n minus 1 and then stop after you've done R choices. So the original definition of it is actually the only correct way to program it if you're ever going to program it. But the mathematical definition, which is extremely inefficient, is like that. Okay, and then now in terms of letters, this actually represents how many words you can make. Let me think about this. How many words you can make that have 3 distinct letters like A, B, C, for example, and then they have 5 ones that are not chosen, like that. So remember when we talked about the word Mississippi? How did we calculate how many total words you can make out of the word Mississippi? We just took all the letters on the top, which there be. Oh, I did 6 ends, my fault. Just kidding. Only 5. So how many unique words could you make out of the letters A, B, C, and N? How many unique words could you make? By using the process we learned last time about Mississippi. I said that you should count how many letters there are. If there's 8, put that on top. And then if there's any duplicate letters if there are any duplicate letters in the word, count how many of each of those there are and put the factorial of each duplicate letter in the bottom. There's only one duplicate letter, which is N. How many N's are there? 5. So you put 5 factorial in the bottom. So all of these things can still be expressed with imagining that you're taking a word and you're putting letters in the word to represent everything. So the unique people, the president, vice president, the secretary, they're represented by A, B, C. And then the people that are not chosen are represented by the same letter as each other, because they're not elected to positions. They're just all classified as the same thing, not being chosen. So that's why they're all the same letter. So the number of words you can make out of A, B, C, N, N is also another definition of the permutations of 8, choosing 3 out of them. Now let's talk about combinations, C and R. And by the way, there's an abbreviation. No, there's not an abbreviation, never mind. Combinations, if you have C and R, this is called choose R out of n things. Or sometimes that they just call it n choose r. In fact, if you go to Google and you type in like 10 choose 3, it understands what that means and it'll calculate it for you. So if you have combinations, let's say that you had 17 discrete math students, for example, and I wanted to choose 3 of them to go to a special conference. Oops, I didn't make them to like see me looking at them. Okay, so then combinations, how many ways are there to choose 3 of people from like a discrete math class of 17 people? I don't even know if this has 17 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. Yeah, it does actually. I guess that was a Freudian slip, I guess. So 17 people. How many ways are there of choosing them out of the group? So let's define this first as a word. So we're not electing them to be specific, different, unique roles like ABC. We're just choosing them to just be chosen, right? They get to get, they either get to go or they get not to go. So this would be like saying a word with like 3 letter C's, and then you'd have how many people are not chosen if you have 3 people chosen and you have 17 total? 14, right? So you have 14 letter ends, dot, 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 like that. So how many words are there to make using the same process for the word Mississippi? Well, you'd have 17 factorial, and then you'd have 3 factorial because you have 3 duplicate C's, and then you have 14 factorial because you have 14 duplicate letter ends. So there's 3 chosen, 14 not chosen. That's basically saying how many ways are there to make a word out of 3 letter C's and 14 letter ends, which would be 17 total factorial, then 3 duplicates, and then 14 duplicates on the bottom. And so the formula for n choose r is in general equal to n factorial over r factorial. Whoops, I wrote an n by accident. And then n minus r factorial. So it's almost the same as the formula for the permutations formula, except there's one more term in the bottom. There is r factorial in the bottom, as well as n minus r factorial. By the way, which is bigger? In general, which is not always, but usually, which is bigger? This result or this result? Yeah, the top one's usually bigger because it has a smaller denominator, which makes it a bigger fraction, bigger total thing, right? Okay, now we're going to learn about something called the binomial theorem. So this is going to be really cool. X plus y to the nth power. I want then before I write this down, there's one more symbol I need to teach you. The combinations formula is so common that not only do they choose the n choose r, but to shorten it down even more, it's also called CNR is also just called n on top, r and bottom in parentheses with no fraction. So it looks like a fraction, but it's not a fraction. It just has parentheses around it. It almost looks like a matrix or something, but you see a parentheses like these, 2 numbers like n and r on the top and bottom. That also just means the combinations of n choose r. So x plus y to the nth power is kind of cool actually. So it's equal to x plus y times x plus y, etc. times x plus y, and there's n total factors, right? N different factors. So how many of those factors, how many times will you get up? How many times will you get exactly? So by the way, when you multiply these out, you're gonna have to like multiply x times x times x times blah, blah, and then you'll have to multiply x times x. So basically, every time you're multiplying everything through, you have to pick one or the other letter in each term and multiply it all the way out. And there's actually 2 to the power of n different possible combinations of things that you can pick. So there's many different many different multiplications that will happen. But how many times will you get x to the power of 3? How many times will you get a term that has x to the power of 3 when you're multiplying all those things together? What do you think? So that's the same as the number of ways of choosing. If you have a group of n things, how many ways are there to choose? 3 times the letter x. How many times will you get x to the third? You'll get n choose 3. There'll be n choose 3 times that happens. Or in other words, it'll be n3 if I write it like that. So if you remember that, that's how many times you'll come up with that term. If you add all those like terms together, let's say if that happens 25 times, then you'll get a term 25x cubed in that. Right? What's the biggest power of x you can possibly get? What's the biggest power of x you can possibly get by multiplying n factors of x plus y together? What's the biggest power of x you can possibly get? Is it x to the nth, right? Because you can't obviously get any more than x to the nth because you don't have that many x's to multiply. What's the smallest power of x you could get, possibly, out of that term? Well, actually, you could get none, because there's going to be one term in the thing that only has y's multiplied together, right? At the very end. No x's, just a y. So x to the n is the first term, x to the 0th is the last term, and so x plus y to the nth power is actually equal to the summation from n equals 0. Whoops, I can't use n because n is already defined. What's a different letter besides n? K, so let's say k. From k equals 0 through n of x to the power of k, and how many times do you get x to the power of k? You get an n choose k, right? Oh, and then I forgot about the letter y. Every time you get a power of, let's say, 3 of the letter x, how many powers of the letter y would you have to have? Well, every time you don't get an x, you always get a y instead, because every single factor has an x or a y in it. So this would be x to the n, the y to the power of n minus k. What's that? That's called the binomial theorem, and we're going to use that several times next class. So that's all for today. So keep up the good work. And by the way, if you didn't hear yet, you can take your test and meet me in my office hours sometime and make corrections to it for half credit. But I have to explain to you how to do it and everything like that, just to make sure that you really actually could understand it clearly for the final. And you have to write down the correct process of how to do it on some either scratch paper or on your test again. All right, well, what? Yeah. That was all.
I was gonna ask if you're at 2 for all, so.
At